Hi everyone, welcome to our last online lesson for chapter 6, and we are in our notes, and in our notes it's called 6.5 and 6.6 together, and we're looking at optimal solutions. So in 6.4 we were introduced to what's called an optimization problem, and we had to write out some variables for a problem, so define our variables, and then we had to state our restrictions, state our constraints, and then finally come up with what's called an objective function. So this BRCO in your notes helped us to remember the order of what we need to do when we're dealing with an optimization problem. Once we've graphed the constraints are limiting conditions in our problem, and we graph them. And once we graph the constraints, we have a feasible region or a solution set, and that's the overlapping area where however many constraints that we graph, let's say it was 2 or 3, we look for the overlapping shaded area. And that overlapped shaded area contains all the possible solutions for our problem. I'm going to take us back for a moment to our notes in 6.4. So in our 6.4 notes, we did an example, and you don't have to open it. I'm going to open it up for you right now. But we did example 1, which was an optimization problem, and we set our variables, restrictions, constraints, and objective function. And it looked like this. Okay, well, here was our problem for example 1 in 6.4. We had this question where a refinery was producing heating oil as well as gas, and we defined our variables as G and as H in millions of liters. Okay, we set our restrictions, and then for each constraint in the question, we made a linear inequality for each one. So in total, we had 1, 2, 3 constraints, and we were able to graph those 3 constraints because we know our solution has to fall within the limits of our problem. So within those 3 constraints, our solution will be somewhere in there. And then we had this objective function that we came up with, and the objective function relates the quantity that we want to maximize or minimize. In this example, we wanted to maximize revenue. So we had an equation that relates that quantity we want to maximize, which is revenue, to the other 2 variables. And in this case, our variables were G for liters of gas and H for liters of heating oil. And we knew the price of gas and we knew the price of heating oil. So we came up with this objective function. Revenue is equal to $1.10, which is the price of gas, times liters of gas, plus $1.75 times the number of liters of heating oil. Okay, and the $1.75 was the price of heating oil. And so what we found when we graphed it is we get this graph that looks like this. And we graphed this together last day. We set up the 3 constraints again, and this time we graphed them. Okay, and we got a graph that looks like this. And the overlapping shaded area was this small triangle down here, and we call this the feasible region. It's the solution set. There's 3 lines on the same graph, so this is a system, and this little area right here is where our solution lies. There's lots of possibilities. We could have a solution right here. We could also take a solution right there. Okay, so any points in this shaded area are possible solutions. So I'm going to come back to our notes, and we're just keeping in mind this graph. And let's draw a quick little graph for ourselves. We don't have to do a full graph, but just up in the corner here, this is what that shaded region looked like. So one of our constraints was like this, and we had a line. Okay, it looked like this. In other words, we had a little triangle. Our feasible region was this tiny little triangle like this. Okay. What's really interesting for an optimization problem is that your solution, your optimal solution, the best solution, is always going to be one of the vertices, in other words, one of the points where your constraints meet. So in this case, there's three constraints and they form a triangle. And sorry, my vertices should be right there. Okay. And so these 3 points of the triangle, the 3 vertices, will give me 3 possible solutions, and one of them will be the maximum solution, and one of them will be the minimum solution. Okay, so we know what is true is that we don't have to spend a bunch of time looking in the middle of the shaded area and just randomly picking points and testing them. Our answer is always going to fall on one of the vertices. So where are constraints when they're graphed, where those lines cross. Okay, so going to this example then, in example 1, when we graphed it, we found that we had one vertice here at this point here was 0, 6. Down at the bottom, this point was the point 0, 0 on our graph. Okay, and this point up here was the point 3, 6 on our graph. This point right there. Okay. So without graphing it again, there's a quick sketch for us. So that's what it looked like. Okay. Let's put those points in here into our notes. So we've got the point 0, 6, 0, 0, and 3, 6. And we should remember that we graphed on our graph was, we graphed G as our, let's go back to our graph just for a moment. Okay, G was our y-axis here, and it was in millions of liters. Okay, and H was our x-axis, and it was in millions of liters as well. So these points represent G first and then H. That's the coordinates of the points. Or sorry, H and then G, X and then Y. So if we come back to our notes, I'm just going to write that above for myself to keep it organized. Okay, so remember that a point on the graph, okay, is written with H first, which is the same as an X, and then G. Okay, next. And we should also make a note to ourselves, remember that G and H were in millions of liters. Okay. So the answer to a question, which is which of these 3 points, which combination of gas and heating oil in liters will give us the maximum revenue? That's our question. Okay, so which of these points might be the combination that will minimize revenue? Okay, minimize means give us the lowest value. Okay, the lowest value for R. R stands for revenue. And which of these will give us the maximum, so the highest? And obviously we want to maximize revenue if we're a company. And so what we can do is we can plug in each of these points into our objective function. You might just look at it and take an educated guess. And you might think to yourself, well, if I look at the first point, 0, 0, I know that if I made no gas and no heating oil, if the refinery didn't produce any, well, I wouldn't have any money, right? So that might be a good guess that would be the lowest value for R. Okay, so just an educated guess would probably be 0, 0. Okay, which of those other points then, 0, 6 or 3, 6, would give us the most money or the maximum revenue? Well, between the 2 points, I would guess that this point right here, okay, or this point here on my graph would give me the most money because I'm producing the most amount of gas and heating oil. If I produce 3 million liters of heating oil and 6 million liters of gas. So an educated guess would be 3, 6, but you don't have to guess. You can actually check and verify mathematically. So if we want to check the vertices of our feasible region, we can simply take all the points, okay, and substitute the values for those points into our objective function. This was our objective function for this problem. It was revenue is equal to the cost of gas, so $1.10, times the number of liters of gas, plus the cost of heating oil, $1.75, times the number of liters of heating oil. Okay, and I'll just write a little note here. Recall that H and G were in millions of liters. So when we take the values from the points, we should keep in mind that those are millions of liters. Okay, well here are the 3 points. So here are the places where my lines crossed. 0, 6, 0, 0, okay, and 3, 6. Okay, and remember that a point is always putting the x, the horizontal axis first. So in this case, h before g. Okay, x before y. So when I'm looking at these points, that 0 is h, and the 6 is g. And so what I'm going to do is I'm going to just substitute those values for g and h right into my objective function. So let's test the first one. R is equal to 1.10 times g, which is 6. And here I'm going to say, instead of 6, I'll remember that I am in millions of liters. So we'll say this is going to be 6 million. Okay. Plus $1.75 times h, and h is 0. Or 0 million, but that's still 0. So my answer is going to come out to R is equal to, if I do the math here, okay, the second $1.75 times 0 is 0. $1.10 times 6 million is 6,600,000. Okay, there's my answer. So that would be the revenue that I would get if that was the combination of heating oil and gas that I produced. Okay, let's do the next one here. 0, 0, this one's going to be pretty easy. R will be equal to $1.10 times 0 plus $1.75 times 0. Well, $1.10 times 0 is 0, and $1.75 times 0 is 0, so we simply get $0. Okay, there's my revenue. And the last point, revenue is going to be equal to $1.10, again, times 6, but remember that G and H are in millions, so that's 6 million. Okay, plus $1.75 times 3, but again, that's in millions. Okay, and so my revenue is going to be equal to, well, $1.10 times 6 million is going to give me 6,600,000. Okay, plus $1.75 times 3 million, which is going to give me, so plus 5,250,000. And so my answer here, if I add those two numbers together, I'm going to get $11,250,000. Okay, so that's my revenue for that combination of gas and heating oil. Okay, so looking at it there, just if I do substitute those points into my objective function for revenue, I can now clearly see that this is the smallest. There's my minimum revenue. Okay, and my maximum revenue is over here. Here's my maximum revenue. So the points that will give me my minimum are 0, 0. Okay, and the point that will give me my combination that will give me my maximum is 3 million of heating oil and 6 million liters of gas. And there I have it. Okay. Okay. If we want to verify that our solutions are still within our limits, so we might want to ask ourselves, okay, we came up with these solutions. We're pretty sure that those are correct. We could, as an extra check, plug those solutions into the constraints. Okay, and our constraints were the 3 linear inequalities that we graphed. Okay, so we had the first constraint that we had was G has to be greater than or equal to 2 times H. That was the first constraint that we graphed. The next one was H, heating oil must be less than or equal to 9 million. Okay, and the last one was G must be less than or equal to 6 million, because we were told in the question, okay, that we couldn't make more than 6 million liters of gas. We couldn't make more than 9 million liters of heating oil. And we knew that for every liter of heating oil that we made, we could make at least twice as much gas. And so those were the three constraints that we had. Okay, there's our constraints. So what we could do is we could plug in our points that we've said are our solutions. Our max, for maximum revenue, the point that we had was 3, 6. Okay, and that's equal to H and then G. Okay, and our minimum was 0, 0. Okay, and that's equal to H first and then G. So I could plug in that point into my constraints, and it should satisfy all of my constraints. Okay, so we can do the first one. Let's go ahead and do that. So G has to be greater than or equal to 2 times H. So G here is 6. Okay, so 6 or 6 million. If I should keep in mind that I'm talking about millions of liters. So 6 million must be greater than or equal to 2 times H, and H is 3 million. Okay, and so what I'll get here is 6 million on the left is greater than or equal to 2 times 3 million is 6 million. And that's a true statement because 6 million is equal to 6 million. Okay, so that's true. So first of all, that point satisfies one of our constraints. The next one I can do here is H has to be less than or equal to 9 million. Well, H is 3. Okay, so 3 million must be less than or equal to 9 million. Is this true? Is 3 million less than or equal to 9 million? Well, yes, it's less than, and so that's true. Okay, so it satisfies that constraint. And the last constraint I have is that the liters of gas have to be less than 6 million. Well, gas was in my maximum, gas was 6. Okay, so 6 million is less than or equal to 6 million. Yes, that's true. 6 million is equal to 6 million, so that's true. Okay, and so far my maximum point satisfies all my constraints. Okay, and so the point 3.6 or 3 million liters of heating oil, 6 million liters of gas gives me my maximum revenue, and I know that my answer, my solution, is acceptable because it meets all the constraints. Okay, and we would do the exact same thing here down below if we wanted to verify our minimum solution, our 0.00, with all of our constraints. Okay, I'm just going to, again, write down my constraints and then just verify. Remember, verify just means to test something. Make sure that it's true. If it's not true, it's not valid. It's not an appropriate solution. And so this time I'll put in the 0.00 for H and G. So 0 is greater than or equal to 2 times 0. Well, 0 is greater than or equal to 2 times 0 is just 0. So this is a true statement. Okay, in other words, this point checks out. The next one, H, is going to be 0 here. Okay, is less than or equal to 9 million. Well, it's true. 0 is less than 9 million. So that's true. Okay, and finally, G is 0 for this point. And 0 is less than or equal to 6 million. Yes, that's true. Okay. 0 is less than 6 million. So this is an extra check that we can do. We can verify the points that we took off our graph for a maximum or a minimum solution, and we can just run it through our constraints and make sure that it's acceptable for the limits that were set on the problem. All right, here's a summary for you, just to kind of put this all together. This is a lot of information, I know. Okay, the optimal solutions. Okay, remember that optimal is another word for the best. Okay, or the in this case, if it's something they're trying to maximize, it'll be the greatest solution. okay, or the least solution if it's something you want to minimize. So the optimal solutions, the max and min solutions, to the objective function, remember this is just an equation, for some quantity that you want to maximize or minimize. Okay, so for example, revenue or maybe cost. Okay, there's something that you want to keep low or you want to have as high as possible. And the optimal solutions for that equation are found at the vertices of the feasible region. So that feasible region is your shaded area where all of the shaded areas overlap, and you're looking for the points where those lines that you graphed cross, okay, the vertices. Sometimes they may not be right on the vertice if one of your lines was a dashed line. Okay, so for example, if one of your constraints was a strict inequality, and when you graphed it, you graphed that constraint with a dashed line, when you graph it, one of your points will be an open data circle. Okay, I'm going to do one of these examples in just a moment. So if we had a dashed line, okay, well, the point where it crosses another line, the point of intersection, will be an open circle. So we know we can't use that point as a possible solution. So if we see an open circle, the solution will be nearby. Okay, so very, very close to whatever that that point was. So whatever the XY coordinates were, it'll be very close to it. Okay, how can we check if we've got the best solution? Well, we can always test each point, okay, off our graph, so the coordinates of the vertices, check them with the objective function. And remember, your objective function is just an equation. So you're just simply going to substitute okay, the point, so x, y, or whatever the variables are, okay, into the equation that you wrote for the objective function. We can also verify those points by testing the constraints. So we can also substitute, once we've found our maximum or minimum solution, we can take that point, okay, substitute that point into all the linear inequalities that we wrote for the different constraints. All right. I'd like to show you two examples where you have a vertex or a point, an intersection point, that would not be included, that has an open circle. So on your next page of your notes there, I use the example in the textbook, and if you have your textbook handy, you could pause this and grab it. If you don't, that's okay. I'm just going to sketch it for you right now so you can see what it looks like in your textbook. Okay, so on page 334 of your textbook, there's two models, Model A and Model B. And if we have a look, Model A looks like this. I'm just going to sketch it out for you. Okay, so they give us a graph that has already been graphed, and it looks like this. Okay, there's a line here, a solid line here. Okay, and then there's this dotted line, dashed line. Sorry, not dotted, dashed. Okay, so that means that anytime a dashed line crosses a solid line, we use an open circle at the point of intersection to say that point's not included. So these 2 points here on your model are not included, but this one is included. It's a solid dot. And here are the coordinates of the points. Okay, so the first one is -4, 3. Okay, down at the bottom, it's -4, -12. And up at the top, it's 11, 3. Okay, and so this is a graph of x versus y. Okay, so the points, let's rewrite them below for ourselves. Okay, the points are x and then y first. Okay, and they are -4, 3. Okay. I'll leave a little bit of room here. 11, 3. Okay. And -4, -12. Okay, so those are the 3 points that we see from our graph. And we're also given the objective function, and this is important, so I'm going to write this up here. The objective function is this. Okay, the objective function, which is always an equation that relates your variables, so x and y, to the thing that needs to be maximized or minimized. Okay, and in this case, this is the objective function you're given. T equals 2x plus 5y. We're not really sure what t stands for. Okay, we're just given variables. We're not given any context to this problem, but we could imagine it's like, it could stand for, maybe t does stand for cost, something like that. Okay, but what we know is that t is related to x and y by this equation. Okay, and we're trying to look to see which of these 3 points will give us the maximum value of t and which one will give us the minimum value of t. Okay, so you could, just by looking at the equation, take a good guess. Okay, you might take a guess that this point up here might give you the max. That's a pretty good guess because they're both positive values, 11 and 3. So x and y would both be positive values, and we get a pretty big number for t. And you might take a guess that this one over here, okay, a negative and another negative will give me the minimum, and those would be really good guesses. We can also check them by plugging those, all 3 points, into our objective function. So let's do that. Let's test. Okay, we're going to test our points, our solutions. Okay, by plugging them into the objective function. So plug into our equation, our objective function. Okay, and I'm just going to make myself a little chart here. I've already got my points up above, but okay, I know my objective function. It's written up there. There's my 3 points. I'm going to write them out again. We've got -4, 3, 11, 3, and -4, -12. And so what I'm going to do is I'm just going to plug in those values. Remember that x comes first and then y. Okay, and I'm going to plug those in to my objective function. So t is equal to 2x plus 5y. So 2 times -4 instead of x. I'm just going to plug in the values of x and y into my equation, plus 5y, and this time instead of y I'll put the 3 because there's my y value. Okay, so we get t is equal to, well, 2 times -4 is -8 plus 15, 5 times 3. So t is equal to, well, -8 plus 15 is the same as 15 minus 8, and my answer is 7. Okay, so t is equal to 7. That will be my value of t for this first point. The next one will be t is equal to, again, 2x plus 5y. So this time we'll say 2 times 11 plus 5 times 3 instead of y. And that's going to give me, well, 2 times 11 is 22 plus 15. So t is equal to 22 plus 15, which is 37. Okay, and there's my value for the second point. The last point here is -4, 12. So I plug those values into my equation, my objective function. T is equal to 2 times x, x is -4, plus 5 times y, and y is -12. Okay, and I do the math. That is going to be t is equal to -8. 5 times -12 is -60. So -8 minus 60, t is equal to -68. Okay, that's going to give me the very lowest value. And so if I look at these 3 values of t, the maximum value I have for t is here. Okay, the minimum is this one. So if I go back to my points now, and there's my 3 points that I have up above, okay, I can say that the maximum solution, okay, is going to be this point right here, 11, 3. Okay, so this was indeed my maximum solution on my graph, 11, 3. Okay, so let's just go over here at the bottom of your page Okay, here's our answer to this question. So the max solution is the point 11.3. That gives us the greatest value for t. Okay, and that point was a solid dot, so it's exactly 11.3. Okay, the minimum solution is, well, let's come back here again. We said this was our minimum solution, the point negative 412. But if you look at your graph up here, there's the point negative 412. It's an open circle, so that point is not a possible solution. What I'm going to say instead is the minimum solution is near, okay, negative 4, negative 12. So that's just the only difference here is it might be negative 4.1 and negative 12.1, or it might be negative 3.9 and negative 11.9. It's really close, but it just can't exactly be that point because that's not a possible point. Only because one of my constraints was a dashed line, and that tells me that it's a strict inequality. And so if I had the original constraints, which I don't, but if I plug the point negative 4, negative 12 into all three of my constraints, because I have 3 lines, there would be one constraint that it wouldn't satisfy. Okay, and so I just have to be a little bit, I have to be close to that, but I can't be exact. Okay, and in this case, if we actually look at it, because the shaded region is here, okay, if I were to take a guess, I can see I'm going to be, if this is my y, and my x-axis is going the vertical direction, it looks like it's going to be closer to about negative 3.9, and a little bit further to the right here, so it'll be about maybe negative 11.9. That would be a good guess for near a nearby point. Okay. Model B gives us this. It gives us an objective function, and this one I don't believe gives us a graph. Okay, I don't have my textbook right in front of me right now, but we don't even need a graph, okay, all the time if we're told a little bit of information about the points. So here's the objective function, 3x minus 2y. So that's the equation that tells me that I want to either maximize or minimize n, which could be the number of, I don't know, apples and oranges, or something that x and y represent. Okay, and that is the equation that I'm given. And here are the points. Okay, the points, and again, x first and then y, they are 0, 9, okay, 5, 4, and 0, 4. Okay, and all 3 of them are open circles. Okay, they are all open points or open data points, which means that they are not included as possible solutions. But we know that those are the 3 vertices, so our solutions must be very close to those points. Okay, and one of them will be our min and one will be our max. You could eyeball your objective function and say to yourself, well, which of these points would give me the greatest value for n, and which of these points would give me the least value for n? Okay, and notice if you're eyeballing it, notice that y here is being subtracted. Okay, so notice that when we plug these values in, notice that we will subtract 2y. Okay, so whatever value y is here, so if we look at these 3 points, we've got 9, 4, or 4. Okay, we can see that when you subtract 2 times 9, that's going to be a bigger negative number. It's going to be negative 18, versus when we subtract 2 times 4, which will be negative 8. Okay, so we might guess, you might take a guess already and say, maybe this one will be my minimum, because it'll give me the smallest number. 0 minus 18 is negative 18. Okay, and my maximum will probably be this point right here, because I will have a bigger value for x, which will be positive. Okay, and I'll be subtracting 4 times 2. Okay, so those are good guesses. You don't always have to prove it. But if we wanted to check, we could do that. Okay, so we could just check. And by checking, I mean substitute the points into the objective function. So let's go ahead and check. I'm going to make 3 columns here. Okay, 1 for each point. So the first point is the point 0.9. The next point is 5.4. And the next point is 0.4. And I'm just going to plug those values for x and y into that formula that I was given, n is equal to 3x minus 2y. So plug them into our objective function. N is equal to 3 times x, in this case x is 0, okay, minus 2 times y, y is 9. So n is equal to 0 minus 18. So n is equal to negative 18. That's the value of n for the first solution. The next one will be n is equal to 2 times 5, okay, minus, sorry, 3 times 5, sorry, minus 2 times 4. Okay, so n equals 3 times 5 is 15, minus 8, n is equal to 7. Okay, and the last one here, n is equal to 3 times x, which is 0, minus 2 times 4. So n is equal to 0, minus 8, n is equal to negative 8. So I plug them into my objective function, and now I can actually see the values of n. This is my minimum. Okay, so I did take a good guess. I was correct. Okay, there's my minimum. And my maximum value, well, the biggest value that I have is 7. That's the most positive value that I have. The other two values are both negative. So there's my maximum value for n, which means that the 0.54 was my maximum solution. And this was my minimum solution. And again, because these are all open circles, I'm told that these data points weren't included. And if I had a graph, I would see them as open circles. So my final answer, if I could write it right below, is that my maximum solution, so here's my answer. Okay, so the maximum solution is, and I'll just say near, okay, the 0.54 instead of at 5.4. Okay, and the minimum solution, the combination of x and y that gives me the lowest value of n, is near the 0.09. So if we have dashed lines, strict inequalities, and we can't say that the point of intersection is a possible solution, we simply just say that the solution is near that point. I'd like you to try some of these questions in your textbook on page 341, and it is numbers 1 to 5 to 7, and very similar questions to what we did here, okay, in our notes. So that's it for chapter 6. We're all done. Please do your chapter 6 review to prepare for the test, and thanks for joining me today. Good luck.